Something just happened on the sun, and it is already heading toward Earth. Not a rumor, not speculation. A real solar eruption. A massive explosion of energy and plasma launched from the surface of the sun is currently traveling through space at millions of miles per hour. And depending on its direction, its strength, and the orientation of the magnetic field inside it, the effects could range from spectacular auroras visible across the world to disruptions in GPS, radio communications, and in worse cases, power infrastructure. In this video, I am going to explain exactly what happened, how these events work, what they do on their way to Earth, and honestly, what you should and should not be worried about. No exaggeration, no doomsday, just the real science, explained clearly. Let's go. First, what actually happened on the sun? The sun is not a calm, smooth ball of fire. It is a violent, constantly churning plasma engine held together by gravity, powered by nuclear fusion, and wrapped in magnetic fields that twist and tangle and eventually snap. Those magnetic field lines are the key to understanding solar eruptions. Deep inside the sun, charged particles flow in enormous currents that generate magnetic fields. Those fields rise up through the solar interior and break through the surface, the photosphere, forming concentrated regions of intense magnetic activity. When those fields get tangled and stressed enough, they suddenly snap into a lower energy configuration. That process is called magnetic reconnection. And when it happens explosively, it releases a staggering amount of energy in a very short time. That sudden release is a solar flare, an intense burst of electromagnetic radiation, X-rays, ultraviolet light, and radio waves, all firing outward from the eruption point simultaneously. But flares are only part of the story. When magnetic reconnection happens with enough force, it can also hurl actual physical material into space. Billions of tons of plasma, superheated ionized gas, are violently expelled from the corona, the sun's outer atmosphere, at speeds ranging from hundreds of thousands to several million miles per hour. That is a coronal mass ejection, a CME. These two things, the flare and the CME, are related but distinct. They often happen together, but not always. And they have very different effects on Earth because they travel differently. The flare's radiation, X-rays, ultraviolet, radio waves, travels at the speed of light. It reaches Earth in 8 minutes. By the time you know a major flare has happened, its radiation has already arrived. You cannot outrun it. You cannot prepare for it in real time. It is just there. The CME is the slow one, a wall of plasma and magnetic field expanding outward through space, millions of miles across, sweeping up material as it goes. Depending on the speed of the eruption, a CME takes anywhere from 15 hours to several days to reach Earth. That travel time is what gives forecasters their warning window. That is what makes the difference between chaos and preparation. Now let's talk about what these eruptions actually look like on the scale of the sun, because the numbers are genuinely difficult to comprehend. A large CME can release the equivalent of 1 billion hydrogen bombs worth of energy in a few minutes. The plasma cloud expelled can weigh several billion tons, and it expands as it travels. What starts as a focused eruption near the solar surface blooms outward into a structure that can be hundreds of millions of miles across by the time it reaches Earth. Solar flares are classified on a letter scale: A, B, C, M, and X. Each letter represents a 10-fold increase in X-ray energy output. An M-class flare is 10 times more powerful than a C-class. An X-class flare is 10 times more powerful than M. And within the X-class, the scale goes up with no upper limit. The most powerful flare ever measured was an X-28 in 2003, and the sensors saturated. The true number was probably higher. In January 2026, the sun released what became the strongest solar radiation storm in over 20 years. An X-class flare triggered a coronal mass ejection that hit Earth and produced auroras visible across Canada, much of the United States, and Europe. The infrastructure held. Power grids were warned. Satellites went into safe mode. Airlines rerouted flights away from polar routes. And the northern lights appeared over places that had not seen them in decades. That is what a major event looks like in the modern era when we have advanced warning and protective systems in place. But we have not always had those systems, and history shows what happens when we do not. In March 1989, a solar storm struck Earth that caused the Quebec power grid to collapse in 92 seconds. More than 6 million people in Quebec lost power. The outage lasted for 9 hours. The geomagnetically induced currents, electrical currents that solar storms can drive through ground-based infrastructure by distorting Earth's magnetic field, overloaded transformers and tripped circuit breakers faster than any human operator could respond. The Quebec event is the reference point that power engineers still use when designing grid resilience today. And it is not even close to the worst case. In September 1859, a solar storm called the Carrington event struck Earth. The telegraph was the most sophisticated electrical technology on the planet at the time. Telegraph operators reported sparks flying from their equipment. Some papers on desks caught fire. Operators who touched the lines received electrical shocks. In some cases, telegraph systems continued operating even with their batteries disconnected, running entirely on the geomagnetically induced current flowing through the wires from the storm. Auroras were visible from the tropics. People in the northeastern United States woke up in the middle of the night thinking the sun had risen because the auroras were bright enough to read by. If a Carrington scale event hit Earth today, same storm, same energy, but striking a planet with 8 billion people whose financial systems, navigation, communications, medical equipment, agriculture, water treatment, and transportation all depend on electricity and GPS, the consequences would be categorically different. A technical report published in January 2026 from the UK's Science and Technology Facilities Council laid out what a worst-case scenario would look like in the modern era. Widespread satellite navigation outages, radio blackouts across entire hemispheres, potential damage to large transformers, the specialized multi-ton equipment that steps electricity up and down for long-distance transmission that can take years to manufacture and replace. In the May 2024 storm, the strongest in over 2 decades, a loss of satellite navigation alone caused an estimated $500 million loss to the U.S. agricultural industry in a single event. We are more vulnerable than we have ever been, not because the sun is more dangerous, but because we have built an entire civilization on top of systems that solar weather can reach. So how does a solar eruption actually affect all these systems? Let me walk through it in order because the timing matters. The flare fires. Radiation arrives at Earth in 8 minutes. The first effect is radio blackouts. X-rays and ultraviolet radiation from the flare slam into the ionosphere, the upper layer of the atmosphere that reflects radio waves around the planet. When that layer gets flooded with high-energy radiation, it absorbs radio waves instead of bouncing them. High-frequency radio, the kind used by aviation, ships, military communication, and emergency services, goes out on the side of Earth facing the sun, immediately. No warning, just silence. GPS is also affected. GPS works by timing signals from satellites precisely. The ionosphere slightly delays those signals, and GPS receivers are calibrated to account for that delay under normal conditions. When a flare disrupts the ionosphere, the delay changes unpredictably. GPS accuracy degrades. In severe events, signals become unusable. During a major solar event in 2006, an X-class flare directly interfered with GPS signals being received by ground-based systems. Then, hours to days later, the CME arrives. When the plasma cloud hits Earth's magnetic field, it compresses the magnetosphere on the side facing the sun and stretches it into a long tail on the night side. This distortion drives electrical currents through the magnetosphere that find their way down into the upper atmosphere and eventually into the ground itself. And from the ground, those currents flow wherever conductors are available, which in a modern civilization means power lines. Long, high-voltage transmission lines stretching across continents act as enormous antennas picking up geomagnetically induced currents. These currents, which are effectively unwanted DC electricity flowing through a grid designed for AC, can saturate transformers, cause them to overheat, trip protective systems, and in severe cases cause physical damage that takes months to repair. The longer the power line, the more vulnerable. North America, with its extensive high-voltage transmission network and large areas of low-conductivity rock geology that amplifies induced currents, is particularly exposed. Satellites face their own category of threat. The expanded disturbed magnetosphere changes drag conditions in low Earth orbit. In February 2022, SpaceX launched 49 Starlink satellites directly into a geomagnetic storm. 40 of them re-entered the atmosphere and burned up because the increased atmospheric drag at low altitude caused them to lose altitude faster than their thrusters could compensate. 40 satellites. One storm. Gone. Charged particles from CMEs also penetrate satellite electronics directly. Radiation damages solar panels, degrades circuits, and can cause what engineers call deep charging, where static electrical charge builds up inside satellite components until it suddenly discharges, damaging or destroying hardware. Satellite operators have procedures for putting spacecraft into safe mode during major events, turning off non-essential systems, reorienting solar panels away from the direction of incoming particles, reducing power consumption. But safe mode is not perfect protection. And then there are astronauts. Human beings in space during a major solar event face direct radiation exposure. The International Space Station has specific sheltering protocols. Astronauts retreat to the most heavily shielded modules when a storm is coming. The Artemis II crew, flying to the moon and back in April 2026, was monitored for radiation exposure every day. Each crew member wore a personal dosimeter. 6 radiation sensors were placed throughout the Orion capsule. The Sun was near the peak of solar cycle 25, one of the most active cycles in recent memory. In a large enough event, a Carrington-scale eruption, an astronaut caught outside a spacecraft in a spacewalk would have a very short window before radiation exposure reached dangerous levels. Here is what you actually need to know right now. NOAA's Space Weather Prediction Center monitors the sun around the clock. When a flare fires or a CME launches, alerts go out within minutes to power grid operators, airlines, satellite companies, military communications networks, and space agencies. The infrastructure industry has improved dramatically in its preparedness compared to 1989. A Discover satellite sits at the L1 Lagrange point, about 1 million miles from Earth, directly between Earth and the Sun, where it detects incoming CMEs before they arrive. This gives roughly 15 to 60 minutes of final warning before impact. Long enough to protect some systems, not long enough to protect everything. For most people on the ground, the effects of even a significant solar storm are invisible. Your phone probably keeps working. Your home electronics are unaffected unless a power surge damages something plugged into the wall. The real vulnerabilities are at the infrastructure level, the grid, the satellites, the communication systems, not your individual devices. The best outcomes happen when forecast systems work, grid operators take protective action, and satellite companies put spacecraft into safe mode. And that early warning network is genuinely good right now. Not perfect, but good. What we are watching right now is a period of elevated solar activity. Solar cycle 25 has been more active than scientists predicted. The sun is producing more flares, more CMEs, and more complex active regions than the previous cycle. And with every major eruption, the question is the same one forecasters ask every time. Is this one Earth-directed? How fast is the CME traveling? What is the orientation of the magnetic field inside it? That last one matters more than most people realize. A CME can hit Earth directly and produce only moderate effects if its internal magnetic field is oriented the same direction as Earth's. But if the CME arrives with its magnetic field pointing opposite to Earth's, southward, it merges with Earth's magnetosphere far more efficiently, pouring energy in much more effectively, and producing a far more intense geomagnetic storm. You can predict the CME's arrival. You cannot predict the field orientation until the Discover satellite detects it, giving about 15 to 60 minutes of notice. That gap between what we can predict and what we need to know is the central challenge of space weather forecasting. This just happened on the sun. It is heading somewhere. Forecasters are tracking it. And now you understand exactly what that means. If this video explains something clearly that you've been hearing about but never quite understood, hit like. Share it with someone who would want to know this. And subscribe. When the next major event happens, we will cover it exactly like this. Stay curious.